Here, the total data is 2,84,807, out of which 492 are fraudulent records. Minority data should be given 1 to make the metrics work perfectly, right? Perfectly show the error. If we give 1 to the majority and 0 to minority, right? Accuracy score, F1 score, that precision recall, everything looks big like this, but model may not work. Behind the scenes model may not be working properly. To correctly assess, the minority record should be given 1 because the precision recall scores focus majorly on 1, right? True positives, right? So I have taken this data like this and I splitted the data like this. I have taken genuine records, 60% records, and kept them as a train set. And remaining 40% records, I split them into 2020 and made cross validation data set with 20% genuine records and 50% fraudulent records. 20% genuine records and 50% fraudulent records. I created 2 more sets. Now, using the Gaussian normal distribution, right, probability density function of normal distribution, I am calculating each row's probability. How am I calculating? This cell probability I am getting, each cell probability I am calculating, multiplying all those probabilities to calculate the probability for this row. Like that, all rows I am calculating. Using those probabilities, I can find threshold where exactly the where exactly this non-fraud records range is falling. That is one way. The second way is on the cross validation set I can find out the threshold. Right, there are fraudulent records and non-fraud records. Right, so I can take the non-fraud records and fraudulent records, look at the probabilities, find out the threshold. This is another way. So mostly the theory talks about the second way. You take cross validation data, right? Using the training data, you found a mean and standard deviation. Mean and standard deviation using the training data, 60% of the data. And then using that mean and standard deviation, you find out the probabilities for the data inside the cross validation set. And try to find out the threshold where exactly that 0 and 1 are changing, right? So most of the 0 records may fall into one range and 1 records fall into another range. Use the threshold to find out the probabilities on test set. If that is working fine, use the same threshold on the production also, right? In production, if you get a new record, what you need to do? If you get a new record, what you need to do? In production, right, you're using this anomaly detection algorithm, right? In production, you got a new record, you don't know the why, right? What you need to do? It is a Gaussian normal distribution approach, anomaly detection with Gaussian approach.
Calculate the probability for the new row by calculating each cell's probability. And then
yes, sir. Yes, sir. So to calculate each cell's probability in the production record, do we need mean and standard deviation?
No, it should be from the cross validation, or no, it's from the training set.
Yeah, we need mean and standard deviation, right? So this mu sigma is actually got from this training set. The same thing we'll use it in production also. Okay, for that reason, we are taking mu and sigma from major data, right? Major chunk of the data. Right? When you take major, mean and standard deviation from major chunk of the data, it will satisfy the extrapolation also. We call it as extrapolation, right? Interpolation means take the data, try to predict something inside the data. Extrapolation means take the data, understand the pattern, and try to use that understanding and predict on other data, the outside data, right? That's extrapolation. While doing extrapolation also, we'll use the mean and sigma, right? So do you remember, I think I said we need to create pickle files and move the code to the production. Do you remember that? When you are trying to move the code to the production, what you need to do? If there is a standard scalar, you need to save that into pickle file. If there is a model, we need to save that into pickle file, take these two and apply them onto the data in the production, right? Do you remember that?
Yep, we need to use dump and load methods, right?
Load methods, right? But in here, in anomaly detection Gaussian approach, what are the values we need to move it to production?
Mean and standard deviation.
Yes, very good, sir. Mean and standard deviation are the things we need to move into production. If you know, take this mean and standard deviation, right? Maybe write it into a file, and then load that file, mean and standard deviation. Use that in, basically understanding here are the threshold, mean, and standard deviation. Right? Three numbers we are going to save and use them in production. Threshold, which we found by using the cross validation set, where exactly that 1 and 0 records are being distinguished. Right? Probability threshold, where exactly that 1 and 0 are being distinguished. And then the mean and standard deviation. Three numbers we are going to take. The model pickle file will have three numbers. That's it. On a Gaussian normal distribution, in production. Okay, there is another point we need to understand. Here, we are calculating probability of each cell and multiplying, right? So each probability is going to be between 0 and 1. This is also going to be 0 and 1. Like that, if you have 10 features, all are between 0 and 1. You multiply all of them, it will become a small number. Okay, that way, what happens is for most of the rows, right, the probability may become 0 because each of these languages, right, Python, C, Basic, all these languages will have their own capability in a way to, round the number. Right? If Basic may take 0.000, maybe 4 zeros and 1, and consider it as 0. But Python may take 10 zeros, but C may take 20 zeros. But there is a limit, right? 0 point, after 0 point, right, it may take till 10 zeros and then it may actually round it off to 0, right? That way most of the rows may become 0. To avoid that, right, what we can do is we can apply log to each of these rows probability. When you apply log, what happens? Log x into y is equal to log x plus y, right? So this of log of this one plus log of this one plus log of this one. If you calculate that way, the thresholds will be numbers which are very decent, and you will be able to find out the threshold. Right? The probabilities are going to be numbers which are decent, and you will be able to find out the threshold very easily. Okay. Even though the probability is significant, because of multiplying small numbers, it may become very small number, and you may not be able to distinguish between one record's probability and other record's probability. To avoid that problem, generally we apply log. This kind of a situation will be there in many scenarios. Whenever you are trying to multiply probabilities, it is always suggested to apply log and sum them up. Log of first probability plus log of second probability, and so on, log of nth probability. Okay, this is a general concept which is useful throughout our AI career. Got it? I did not mention it here. I wrote it here, but
So after finding log, then we need to again do the inverse log after the summing up.
no need, ఎందుకంటే we need only the threshold, right? So for each row, for all rows we are applying log.
Okay.
For all rows we are applying log. There will be numbers which are very evident, not close to 0. So in those evident numbers, right, we'll find the threshold. That threshold we'll use. Even in production also, we'll take the record, find out the probabilities, apply logs, sum them up, and see whether the probability is less than the threshold or more than the threshold, more than or equal to. If it is more than or equal to, we'll say no, record belongs to one class, and less we'll say another class. No need to inverse transform because this is not the prediction. This is just the probability to find out whether the class belongs to positive or negative. Ultimate prediction is based on the threshold, right? So it is like I think I kind of induced it before also. It is like this, right? You take probability and threshold, you make prediction. Probability, threshold, make prediction, like that. Got it? No formula, right? This formula, don't look at that. Only this column, you look at the last column. Got it?
Yes, sir.
So there is another formula called as multinomial multivariate normal distribution. Here we are using, Gaussian normal distribution for single variable, each variable, and multiplying them. In some cases, right, total data may be normally distributed. If this formula should be used only when each of the column is normally distributed, right? If the column is normally distributed, we will use this formula. If the distribution is different, a mathematician should find out the probability, the formula, density function, and then use that density function to calculate the probability. That's going to be more appropriate. But this is a Gaussian approach. So for every data set, whether it is normal or not, we'll try to apply this. But if you speak practically, right, we need to find out the probability density function of each column and use that as the probability function, and then calculate the probabilities and multiply. That way it's going to be more accurate. The threshold is going to be more accurate and model is going to work well. In some cases, altogether n variables are going to be normally distributed. All n variables are going to be normally distributed. How to see? I don't know. Okay, so you can use this trial and error, right? Again, in our experimentation also we did trial and error. We used individual um, uh, individual variables probability density function and multinomial density function, and try to see which one is working best. If this is working best, we'll take this one. If not, that one. If one is working well, that means there is that pattern in the data. Okay, so this is a formula to calculate multivariate normal distribution, but no need to remember the formula. We have everything implemented in SciPy. Okay, so let me jump into the code and show you the code, and then if you have any questions, right, we'll discuss. So here, this guy, right, this guy, why am I saying this guy? Hanumantarao is the one who actually did this. He actually worked on this project for almost 1 to 2 months and created this file. Is that difficult? Because initially he was doing it, it is difficult, but you already have it, right? If you try to look at this code or copy paste it and use it, and then try to do some more experimentation, right? Maybe in 1 or 2 days you can get full hold of this whole concept. Okay, so this data set is present on the Kaggle. Somewhere we gave a link. Let me show you. Right, credit card fraud detection. This is a data set, right? You can download this data set from here. Data. Yeah, here. Right. So this is the data. You can download it and then start, using the same code. Okay. And here the columns are like V1, V2, and so on, right? It will be 28 and amount and class, right? Which class it belongs to? 0 class and 1 class. Already those guys have labeled it. This is from a European bank, and the general people shouldn't be looking at the details there. That's where they actually applied PCA on the data and gave it to us. Okay, on the Kaggle, whatever data they kept it, it is all PCA converted data. This is Z1, Z2, and so on. Time and amount, they kept it the real, actual numbers there. Okay, so this is the data, and on this data, use describe, which will actually show you the ranges and if there are any outliers and things like that. And then any nulls are there? No nulls, so no need to be worried. So class value count, right? See this out of this is the class count. 0 class this many records, 1 class this many records. It is definitely an anomaly detection problem. Okay, now this guy actually tried to do histogram for the records belonging to fraud and genuine. Okay, he took all the records belonging to fraud, did a histogram. All the records belonging to genuine class, did a histogram, overlapping each other. Why did he do that? To know whether there is any distinction, right, in the distribution of the two classes. If you see this, is there any distinction between the fraudulent data distribution and genuine data distribution on V15? One column it is. Okay, in one column, right, fraudulent records distribution. In the same column, I think 14, sorry. Right, in the same column, genuine records distribution. Is there any difference between the distribution of the data here between two classes?
Mostly similar.
Mostly similar. Can we use that feature to predict? Can we use that feature which is mostly similar distribution between fraudulent and genuine records?
No, sir, because they are very much similar. I think we
Yeah.
can-
So they will not distinguish. It is like you know, it is like there are 10 minus 3s, you know, belonging to fraud. Again, 10 minus 3 is belonging to genuine also. There are, you know, 20 zeros, maybe, you know, 50 zeros belonging to fraud record and 50 zeros belonging to genuine record also. So the distribution is same. It may not be able to distinguish the class. So, you know, this guy actually did this plot to understand which columns are important and which columns are not important. So your normal your sorry, not normal, your distribution plot is useful in selecting features also. Right? So which wherever it is, you know, completely overlapping, he eliminated those features. So, you know, he wrote some notes here. So V28 to whatever these features he eliminated, and then took the rest of the columns. Time he did not take, right? And amount he took, right? And did some, you know, this is called as pair plot, right? This is a scattered chart. This is not important. I don't see much value there. Maybe in Kaggle somebody would have written it in kernel, you would have copied it. Now this is the most important method. Select threshold by CV. Okay, this is the method we are going to use to find out the best epsilon, that best threshold, where the positive class and negative class are being distinguished. Okay, so I'll come to this method first. Let us see what exactly you know, he did it. So he did multivariate Gaussian and normal, you know, general uh, Gaussian distribution thing also. Splitted data into train test. Right? How did he do that? You know, test size is equal to 0, right? Random state is equal to 0, right? 0.4, sorry. Test size is equal to 0.4, 40%. So he actually took only genuine records and dividing that into 60-40. Okay, because the 60% is going to be used to find out the mean and standard deviation. This 40% is used in the cross validation and you know, test set like this. Okay, he split it again, and then fraudulent records he took. Right, this is for, you know, 50% data, and then you know, then he mixed it. You know, you see the concatenated the genuine CV and the fraudulent CV. This is like, this is 20% of the genuine records and, you know, 50% of the fraudulent records. 20% genuine, 50% fraudulent. Right, created the data sets. And now he is estimating mu and sigmas, right? Mu's and sigmas for all the columns in a single chart. Estimate mu and sigma. In this mean and covariance, but he is using covariance, not, you know, the standard deviation, because in the formula multivariate normal dot PDF, this is in SciPy, is using covariance to calculate the normal in the probability density function of normal distribution. That's where he is using covariance rather than covariance matrix rather than the standard deviation matrix. Okay, depending on the formula, depending on the method we are using, we need to use it. Even though theoretically we need the standard deviation, he is using covariance because of the formula. You look at the formulas, right? You will understand why and how and all that. Definitely, I would suggest you to look into every detail of this. Okay. On Saturday, we should discuss more on this. You guys should actually work on this, and we should, discuss more. So now, right now, after finding mu's and sigmas and all that, right, he is using he is calculating the probabilities. Right, on the cross validation set, he calculated probability. On the test set also, he calculated probabilities of all the rows. Okay. Now, selecting the threshold using cross validation data, right? TCV and Y variable, right? So we have actually done this before also. Whatever I am going to show it here, we have done this before also. But let me show this only. I will not go back. Right? So select threshold will take the probabilities and the Y values. In the cross validation data set, there are 50 56,863, sorry, 56,863 zero records and 200 and odd number of 290 odd records belonging to 1, right? Right? In this, do you agree? In this, in this probabilities, right? In this Y value, there are 56,000 56,863 ones and 290 odd zeros. Do you agree?
Yes, yes.
Right? Probabilities belonging to each of those zeros and ones we have. Now we need to find out where exactly that split is happening. Okay, so select best threshold. Let's go back to that method. So probabilities and Y we have taken. Best epsilon 0, best F1 0, right? F is 0, right? Precision 0, recall 0, best whatever, right? So we can rely on F1 score, and so I have from these probabilities, right? I have taken unique probabilities. Right? NP dot unique, all the probabilities I have taken. But there are 57,000 odd probabilities are there. Out of all, I have taken unique probabilities as epsilons. I want to know which probability is distinguishing the data correctly between 0 and 1. So I have looped through epsilons, right, the probabilities, and then trying to calculate, true or false. This is prediction. Prabhas less than epsilon. You can do a greater than also. That guy did less than. Try out a greater than also and see what happens. Right? Prabhas less than epsilon. Here you will get 57,000 odd true or false numbers, true or false values. Do you agree? Do you agree? Are you thinking along? Right? These are the predictions.
Yes.
Like here. Right? This is the operation we are doing there. Okay. So now we can calculate. Now I have predictions and I have Y value. I can calculate F1 score. Okay, precision score, recall score also I can calculate, but I am not using them. If the F1 is greater than the current F1, the default value I have taken as 0. In the first iteration, it is definitely going to be greater than. So best F1 is equal to whatever Fi calculated here. Yes. Right, best F1 is equal to 0 I kept, right? And Fi calculated here. If that F is greater than best F1 I am making as F1. Right? Precision recall also I am saving, and epsilon I am saving. This is the important thing. Again, going back and trying to take the second epsilon, calculating predictions, calculating F1 score. Is that best? Where exactly the model is working good, I am taking that epsilon as the best epsilon. Right? This epsilon I am going to use in production also. Right? This is the return value. Right? Find out the best threshold. This epsilon is the return value. Did you get it? Simple, right? Did you guys get it? Any questions there? Yes, no. Are we good? Can I move on?
Yes.
Good, thank you. So here, right, I have chosen the best epsilon, and then this guy actually did a precision recall curve. No, this method actually has precision recall curve. I think the code is already having. Yeah, see this plotting the precision recall curve. The precisions and recalls at best threshold he calculated, and he's actually doing the precision recall curve to find out the best threshold again, right? So epsilon, no, maybe we got some number, see the best epsilon. Where is the best epsilon? 0.24. Somewhere here we are getting best epsilon. Okay. So maybe here also 0.3 also we can take, but no, it's going to be balanced 0.8, around 0.8. So on the he took this number, whatever the method gave, not using the graph, whatever method outputted the epsilon, that epsilon he took, and then predicting and printing the F1 score precision and recall. And then on the test set also you would have done. See this on the test set 82, 91, 76. F1 is 82 on the cross validation test set and test set. That means the model is working the best, right? It is not overfitted. The model is working good, right? So this is another in CBON there is a heat map, and give me one second. He took confusion matrix and tried to show it graphically. Okay, so somebody is doing research work, right? Research work, generally guides and other people are very excited to look at graphs, and it's easy to understand also, right? So you can use this code to generate, a beautiful whatever computer matrix. Right. So like that, you can find out this is the model. Right? This is the Gaussian normal distribution model to find out, whether a record is fraudulent or not. A new record comes in, you will use the same threshold, use the same mean and mu and covariance matrix, and try to pass it to the same method. Right? No need to find out the best threshold. Use the best threshold and see whether it is less than or greater than, and depending on that you predict. Got it? Got it? Any questions? Anomaly detection using Gaussian normal distribution. Our statistics, whatever we learned, is all useful. Right? Beyond what we learned, statistics is used. No, very rarely. 99% of the times, whatever we learned is more than enough to handle many situations in AI. Okay. Can I move on? I'll show you. Yesterday Seshiram asked, why can't we use classification algorithms to find out anomalies? We can. That also works. Sometimes that also works best. Random forest works better than this Gaussian normal, whatever. I'll show that in a minute. And there is a concept called undersampling, oversampling. I'll talk about that also in a minute. This will have everything, right? The Gaussian normal distribution and everything it will have. This is loading from GitHub, so that's where it is taking a little time. So here, right, this guy Hanumantrao actually tried to build model with other algorithms also. SGD classifier, logistic regression, right? I think random forest, ADA boosting, right? He tried to use all of them. He took the data, splitted the data 20%, 80%, right? Build and train the model, right? Whatever this right? Model, he is passing the model object and then fitting it. He is actually trying to do with different algorithms, right? So he built a common method where he'll pass the train set, test set, and the model. It will automatically fit it and predict and try to print, right? Like that, he actually built a common code there. And he's having this select threshold also, because he used all the approaches, Gaussian normal and other approaches also in a single file. So let us look at yeah.
Sir, is there any other way to filter out the features or only plotting?
Yeah, there will be other ways also. Maybe you build a SGD classifier and try to do regularization and see which features coefficients are becoming 0 or close to 0, eliminate them. That is one approach. In random forest also we have an approach to select best features. I'll show you. You can use those also. And if you know the business and the actual features, right, you will be able to do it more authentically. Right? Here it's a PCA applied data, right? We don't know what is V1, what is V2, what is V3. Right? We don't know business there. Right? Column names, if you know business, and you can do that way also. Got it?
Yes.
So SGD classifier, right? Ad hoc approach. Applying multiple models to data and looking at the error and seeing whether the model is working good or not. HGD classifier and ensemble model he used. I'll explain what is ensemble model once after random forest, but let us look at it. There is no harm in just looking at the code, right? So HGD classifier he took, and class weight balance, because the data is imbalanced and he is trying to create weight, right? If the if the data is high, there will be a small number multiplying. The number of records are high, there will be a small number multiplying the record. The records are low, there will be a big number multiplying the records. That way, the weight will get balanced. Okay, and take an X train, Y train, trained, predicted. Right, he's looking at classification report. Right, if you look at this, right, if you look at this, right, there is precision recall F1 score belonging to 0. Okay. Now this classification report is another method from scikit-learn which actually shows you 0 records precision recall F1 score and 1 records precision recall F1 score. How is that happening? This is happening when you give majority records 1. This is the precision recall and F1 score. Okay, when you give minority records 1, this is the precision recall and F1 score. Okay, got it? In a classification report, you see generally when you calculate precision recall or F1 score, you will get one number, right? One precision, one recall, and one F1 score. But when you look at classification report, you see there are 2 recalls, 2 precisions, and 2 F1 scores. Right? How they are happening? Did you get it? How they are happening? Did you get it? I explained already. Did you get it? Any questions here?
Yeah, I got it. Based on the confusion matrix, you actually took all the directions, like true negatives. When you take the true negatives, you will get for 0, and for true positives, you will get for 1.
Confusion matrix only, but there are 2 different confusion matrix there. One confusion matrix where you gave all the majority records 1 and minority 0, right? That's when you got this first precision recall and F1 score. Minority record 0, Minority records you gave 0. Majority 1. That's when you got these precision recalls and F1 scores. Now majority 0, minority 1. These are the precision recall and F1 score.
Sir, why was this done? Just for understanding only?
No. Classification report is a method which is present in scikit-learn, and generally some people will try to use this approach, and there is a problem with this. I am trying to go there, but first we need to understand why we got 2 rows of precision recall and F1 scores.
It is clear, sir.
That is clear, right? So majority you gave, minority you gave 0. These are the F1 precision. Minority you gave 1. These are the F1 precision recall. Okay. And if you look at this, yeah, go ahead.
So even though if we give the majority records 1, the minority records 1, a single confusion matrix, we can calculate both, right?
Yeah, both we can calculate.
Precision for 0, precision for 1.
You take, this as the focus and try to calculate precision this direction, recall this direction, you get those, minority 1 thing. If you take this as the basis and take, calculate precision this direction, recall this direction. Oh, okay. You made that point previously. Good. Okay.
Yeah.
I got it. Yeah. This direction you take, then you calculate that. So that, they are taking 0 class as the, focus and calculating precision recall and F1 score. They are taking 1 class as focus and calculating. If you want to understand simply, minority 1, minority 0, and then calculate F1, then calculate F1, right? Whatever, right? Got it, right? No confusion, right? So if you look at this last row, right, it's going to be average of these two. Okay, this should not be done, especially on an imbalanced data set. This should not be done. Many of the reports, many of the PhD reports, right, when you look at papers, right, published by other people, right, many of the PhD reports, they are actually trying to show the average score as the score for precision recall and F1 score. This is the score we should be looking at. If you look at that score, right, precision is very low, recall is high, but F1 score is very low. But the model is not working at all. Okay, you should be focused on this only. When you calculate general precision score, recall score, you will get these numbers only. Okay, in classification report, it is showing everything and the average they are taking. It is not valid thing. Do you agree? This is not a valid F1 score or precision score or recall score. Do you agree with me? Do you agree with me?
Yes, sir.
This should not be done. In many of the publishings, the papers published by PhD researchers, they are doing this. And many of the guides doesn't know that should not be done, and they are taking it as the measure. Okay, they are taking it as the metric, and they are thinking that the model is working best. No, model is not working best. If you look at this, that actually gives you the clarity how the model is working. See this accuracy scores when I try to print F1 score, precision score, recall score, very low, right? SGD classifier is not working well, right? So this guy took alpha is equal to 5. What is alpha? The model is underfitted, right? If you look at this, right, on train set, the model is not at all working well. That means what? Model is underfitted. When the model is underfitted, should we reduce alpha or increase alpha?
Decrease.
Decrease alpha. Yeah, right.
Decrease.
This guy increased it and it started working. When model is underfitted, when model is, if you increase alpha, model will underfit. Decrease alpha, model will overfit.
Alpha is the regularization.
Yeah, regularization parameter, but this, here he took 5 and it started working. It should be kind of 0, right? Make the model. Okay, we'll see this. Maybe you guys try to experiment, right, and then see why this alpha is coming 5. Theoretically, this should be small number. State. Yeah. So he did something, and it started working on the train set, cross validation set, and test set. We are getting equal number of F1 scores and all that. This is a point I may have to think a little bit. Leave it there. Okay. I don't know what this is. We tried to do some precision recall curve here. There is no, the other line is not actually there. Yeah. Yeah, look at it, look at it and see. He used ensemble model also here, random forest classifier, and that actually works best, on the train set 92, F1, the test set 84. This is better than the other models. Yeah, ADA boosting. It is overfitted. Okay, ADA boosting is overfitted. Voting classes. These things we did not cover yet. I'll cover them and then we'll. So there is another concept we need to understand: resampling, undersampling and oversampling. This is the point I wanted to explain. So general algorithms you see, and that point, right? We actually need to play with the code, and maybe he's right, maybe he's wrong. We need to see, right, whether it is right or wrong. That alpha value, we'll see that later. Maybe once one of you experiment with this, we'll see that. So here, the undersampling and oversampling. Right? This is another technique which is used in AI. So we have 2 lakh odd number of records in our data, right? So 2,84,807 records. There are 492 records belonging to 1 and 2,84,315 records belonging to 0. If we want to do undersample, this data set is imbalanced, right? That's where the problem is coming. The model is not able to, I think you see that, right? The algorithm is unable to understand pattern well, and we had to struggle a lot, and that's when we had in the SGD classifier, the model started working well, right? You'd have struggled a lot, then it started working well. So this is the problem. Because of this problem, we went to Gaussian normal distribution algorithm rather than using SGD classifier normal algorithm. These also will work, right? It is not that it is not going to work, but you need to struggle a lot to find out the best hyperparameters to make the model balanced on all 3 sets there. Okay. So there is because of this imbalance, the model is unable to understand. The algorithm is unable to understand. To make this balanced, right, we can do 2 things. One, somehow increase the number of records, right? Try to create these kinds of records, more records, which will be equal to, right? You increase 492 records to 2,84,315. That is called as oversampling. Right? You take this data and create some synthetic data. Right? You try to create the same pattern with 1 as the y value. Right? It may corrupt your data. Right? But that is one technique. Okay? It may corrupt your data. This is called as in bootstrapping. We have seen that, right? So you take the data, split the data into 2 parts, 37% and 33% and 67%. Using that 67%, you copy paste and try to reproduce, right? That is bootstrapping, replacing with resampling with replacement, right? So that is bootstrapping. Like that here also, you try to create some synthetic data which will be equal to number of records of the majority class. That is called as oversampling. Undersampling. You try to pick 492 records from this 2,84,015, 15 records, and try to create a data set with 900, maybe around 1,000 records. That is undersampling. Did you get it? What is oversampling? What is undersampling? Did you get what is oversampling and undersampling?
Oh, can you please repeat, sir? I could not hear fully.
So what you do is undersampling. I'll explain. We have only 492 records here, right? Right. We will choose 492 random records from this zero class. From the zero class, we will choose 492 records randomly and form a data set with around 1,000 records, right? Around 984 records. We will form a data set and try to build a model using 984 records only. That is called as undersampling. Got it?
Yes, sir.
Oversampling means you don't touch the zero records, take the one records and try to oversample them, try to create some synthetic data. You understand the pattern in this axis and try to reproduce that kind of a data and put ones which is equal to this one, which is equal, the count is going to be the, then it's going to become like 2,84,350 plus 2,83,350. It will become a huge data set. That is called the oversampling. Got it?
Yes, sir.
So to do oversampling and undersampling, there are packages. Smart is one package, and there is another.
So which one will give best results?
Depends on data, right? Here, if you do undersampling, it will not work well because you'll be losing lots of data from the zero records, right?
Yes.
Undersampling may not work well, but oversampling may work here. It depends on data. Okay. And oversampling also, if the sampling technique is correct, right, it works best. So this guy uses mode. Let me show you. Yeah, resampling, undersampling, right? This guy took genuine records and fraud record, and he chose, from genuine records, he chose only 492 records, and then formed a 984 records dataset, and then trying to build a model, right? It is working well on the train set and cross validation set, but not on the test set, right? Model is not working on the test set, so this is not useful. And oversampling, right? Oversampling, this is, he copy pasted records here, I think. Genuine records, fraud records, right? So fraud data, HTAG, extreme, oversampling, length. The fraud record 391. Yeah, here he copy pasted the records and tried to create more fraud records. It is a bootstrapping kind of technique. It is, right. So if somebody asks you, is it okay to have duplicate records in your data? What is the answer? Is it okay to have duplicate records in your data? What is the answer?
Better is to remove, sir. Unnecessarily, it will influence the accuracy.
But here we are intentionally creating duplicate records, if you see. Right?
The predictions will work better if the input record is of the same pattern.
Yeah, same pattern, but the model will try to understand the pattern better if you are repeatedly trying to show the same record, right? Similar record or same record. This is a dumb way of doing it. Having duplicates is, depends. On the situation, it depends. All the time you cannot say having duplicates is wrong. Best way to remove the duplicate records and try to see how the balance is between the data, and build the model and see how it's working. If it's not working well, then the minority records you can actually create duplicates and build a model also. This is one way of oversampling. Okay. The other way of oversampling is try to understand pattern in the minority data's X variables and try to regenerate, right? A little bit different data, right? We can write some logic, right? So SMOT is a method which actually does that. Okay. So here, this is a dumb way. We are copy pasting the records to make the data, 78,200 fraud records, and then building a model, right? See this on the train set, on the cross validation set and test set, it improved. See that? Or sampling improved the model's performance, right? So will it work all the time? You don't know. It is a trial and error, right? Generally, overfitting works. So oversampling works than undersampling, because undersampling you lose data, right? You lose data means you lose pattern, right? Here we are repeatedly trying to show the same pattern to the model so that it will focus more on the minority data also and try to understand a little bit of pattern there. Rather, it will ignore the 400 and odd records pattern and try to capture the major records pattern. So if you look at that, if you look at the example, similarity but not the same thing. If you look at that KNN, now K means clustering, sorry, KNN algorithm. There was a column with big number, there is a column with small number. When we are trying to measure the distance, right, the small numbers importance is nullified. So when you normalize the data and then try to build a model, it actually took the importance equally, right? Like that here also. If you try to copy paste more records, the algorithm will try to focus on these records also, because repeatedly they will also come, in iterations, right? Multiple iterations, that pattern will also come. The theta will get adjusted to this data also, right? Thetas will get adjusted. The thetas will get adjusted to this pattern also a little bit. If you have less number of records, right, only less number of times that repeated thing will come. I am talking about gradient descent iterations, stochastic gradient descent iterations. I hope you are visualizing it. Okay. What is happening in stochastic gradient descent iterations? One record randomly picked and the theta is getting adjusted. Another record randomly picked, theta is getting adjusted. When you repeatedly show the similar kind of pattern, the theta gets adjusted to these records also, these 400 records also. Even though there are 400, we are repeatedly creating it, copy pasting it, so that the algorithm focuses on this and the theta will actually move towards this data pattern also. That way the model works best. Got it? Analogy. Having duplicates is always not harmful. Got it? Can I move on?
Yes, sir.
Okay. So now this is oversampling, and there are automatic techniques also. So, SMOT is SMOT. This is a technique, right? It actually simulates the data instead of copy pasting. It simulates, it takes the data and takes pattern, understands the pattern in those 492 records and tries to reproduce more records of, it created a balanced data set. And now you can build a model and model's accuracy will improve more, right? After SMOT, the model is overfitted. If you play with the hyperparameters a little bit, right, the model will become the best, right? So the oversampling, undersampling techniques are very, very useful, especially when handling anomaly detection data sets. Right? Got it? So Gaussian normal distribution model is not the best. That is one of the approaches. And on a imbalanced data set, the oversampling technique worked well. That too with SMOT it worked well. There are 2-3 different ways of doing it. Smart is one way. There is other. There is another. Yeah. Imbalance learn is another module where you can actually use. You can import this and then say oversample and undersample, which will actually create synthetic data. Synthetic data to make the model understand the path. Got it? Any questions? Any questions?
So when we apply log on the probabilities of each individual data point,
Probabilities.
so will that sum be equal to 1?
May not be. May not be. It may not be 1. Basically it should not be 1, right? This is not like, if you sum up the individual probabilities of column, it should not become 1, right? The probabilities of sum of all the individual columns is not 1, right? Got it?
At least for one record, will it be near to?
No. There is no relationship between those individual columns, right? If you assume each column is independent column, right? Each column's probability is its own probability. Each cell's probability is its own probability. There is no relation, right? All of n columns probability sum is equal to 1. There is no condition like that. There is no relation there.
But we are actually using this, right? Using this as a threshold, or using this to
see. Let me try to explain this way. When you are calculating probability using logistic regression for each record, you are calculating probability using logistic regression. Is it becoming 1 for each row? Yes, no, right? It is going to be different, right? So you are using that probability and having some threshold, default threshold 0.5, and trying to make predictions. Like that here also we are calculating. For each row we are calculating some probability using a different approach. Got it?
So for one record, for label 1 record, it may go to near to 1, right?
No. Label 1 record, it may go, it may not go. That's where we are trying to find threshold, right? Because it's a Gaussian normal distribution probability, all the probabilities, right, for all the records probabilities may range between 0 and 0.2. We don't know. Or maybe between 1 and 0.7. We don't know. For 0 records, all the probabilities are going to be close to 0.7, and 1 records maybe probabilities are close to 1, or other way around, right? Maybe between 0.2 and 0.4, right? 0 records near to 0.2, 1 records 0.4. We don't know. This is like an unsupervised way of calculating probabilities. We are not looking at y value and calculating probabilities. Once after calculating probabilities, we are trying to see where exactly the threshold is falling. Got it?
Yes, one more thing, sir. Actually, because each of these
I think Seshiram is not done. Give me one, sir. 1 second.
Just adding clarification.
One more point I wanted to explain. Then you add clarification, right? In our logistic regression, right, the algorithm is always looking at y value. That's where the probability will come close to the 1. If the record's y value is 1, probability comes close to the 1. If the y value is 0, probability comes close to 0, because it is always looking at the y value. Here, it is not looking at the y value. So we don't know where exactly it falls. That's where in a loop we are trying to find the threshold. Go ahead, sir. Girikar.
Yeah, the row's probability will not be close to 1 because each of these term is again is a probability, and
Yes.
it will be less than 1.
Yes.
Like a fraction kind of thing. When you
Yes.
multiply fractions, right, the overall value will
So
still reduce.
what Sishiram is saying, add all these, will you get 1? After applying log or before applying log, add all these, will you get 1? That's what the question
I
is.
think he was asking, add after applying log. Is that correct, sir?
Yeah, he asked after, but I am actually trying to explain in both ways. Before or after adding log, you will not get 1 when you sum up all these probabilities.
Sure.
Seshiram, you got it?
Yeah, before applying log, obviously it won't because it's a multiplication of decimal values.
Yeah.
But after log,
if there is a relation, right? If there is a relation between all the input columns, then you can say whether it is going to give 1 or 0. But there is no relation, right? We are assuming that all the basically, to explain, I am assuming that all the input columns are independent. When they are independent, how can you sum them up and come to a one number, maybe 1 or 2 or 10? When they are independent, right? When you calculate log probability, it's going to be some number for each column, each cell, and you sum up all those, you get some number. You don't know what number it's going to be.
yeah. Let me just tweak the question. I got what you just said.
Yeah.
So all the probabilities of zero label records will fall in some range.
Mhm.
It may be from 0.5 to 1 or 0.7 to 1
Yes, sir.
or 0 to 0.2, and all the one label records probability will fall in one range.
Yes, sir.
Okay. So based on it, we need to whether we say less than or greater than symbol when
Yes.
we use the threshold, right?
Yes, sir. Yes.
Okay.
While experimenting with the threshold method, right?
Yeah.
You need to play with it.
Okay, sir. Good.
Even in our binary class classification class also, I try to show something like this, right, to find out the best threshold and all that, because I played with that there, to show this here, that is that threshold finding and playing with the precision recall scores is very important, right? On an imbalanced data set, it is very important.
There we discussed like the default threshold is 0.5, and if it is
Yes.
more than 0.5, it is the one
Yes.
class. It is
But
less than
we try to play with the threshold also a little bit. Yeah, it's a magnification here. It's a real use here. Okay. So, play with this code if you want. If you want, maybe 1 or 2 days we want to do that in the class also, I'm okay. But definitely you should play with this code and the dataset. If you play with this code and dataset, right, interview becomes very piece of cake. Most of the questions you will be able to answer very comfortably. Theoretically you may know, but when you practically implement, right, there will be hiccups, and the people who interview, right, they would have already experienced, and they'll try to ask questions in that way that the answer should be, when you answer, right, they'll understand whether you actually practiced or just know the theory. Okay, so that's it for today.